Today, I want to give a quick review of everything we've done so far. I want to talk about a new area, Fourier series. And in particular, we're going to give an overview of what this means. And this is all of chapter 17. Then we're going to talk about trigonometric Fourier series. So it turns out that Fourier series actually have three different types. And we're going to start off talking about the Fourier series in the AB coefficient type. And before I begin, does anyone know anything about Fourier, his story? He's an interesting guy. His mother died when he was very young of suicide. His father was a tailor, couldn't take care of him, just pretty much left him on his own. He ended up self-tutoring. So he was very, very poor growing up. He ended up self-tutoring in math. He ended up joining l'École Polytechnique, which is France's military school, and did so well in mathematics that he attracted the attention of Napoleon. Napoleon saw himself as a Renaissance man, and he hired tutors in becoming an artist and a mathematician and many other sciences. Well, he hired Fourier to teach him about mathematics. And Fourier, by all accounts, was a very good teacher. When Napoleon ended up deciding to invade parts of Europe, and it had a battle going on in Africa, he thought he would reward Fourier by making him a battalion commander of an artillery battalion. And so he shipped Fourier off to the shores of Egypt as a battalion commander. Of course, Fourier had no background in military operations at all. And so he ended up, luckily, having a very good platoon sergeant who took care of all of the artillery battery work, while he ended up trying to come up with a theory that explained how these cannons that he was now in charge of wore out. Back then, for all the weight of cannons and as heavy as they were to move, they could only fire about 20 rounds in combat before the bore would wear out unevenly and they'd have to be recast. And they didn't understand very well how physics worked. They thought that the reason why the bore heated up so much and partially melted was because when the cannon was cast originally, they thought the heat of the casting was somehow locked up inside the cannon. When the cannonball flew through it, it would rip away parts of the metal, which did happen, which would then release this latent heat of casting, which did not happen, and that's what made the thing heat up. So although his understanding of physics was totally wrong, he developed this theory of mathematics to explain how heat moves through the cannons, and it's what we're going to study today. It was a really brilliant theory of the time. The idea said that intuitively that you can create any repetitive waveform out of a series of shifted and scaled cosines. Anything. I mean, you can create something that looks like this with just a series of shifted and scaled cosines. So he wrote his PhD thesis about it at l'École Polytechnique when after Napoleon was captured, and his professors at l'École Polytechnique, they were some of the most brilliant mathematicians we've ever had. They included Gauss and Lagrange, and they said, "You're wrong." They said, "Here's an example of a waveform that you say you can model with cosine waves, but there's obviously no way because cosine waves and multiples of cosine waves at different frequencies, they're all very smooth. They look like this. And no matter how many cosine waves you add up, you're never going to have anything in which one piece of the cosine wave is not adjacent to the next cosine wave. But here you've got one piece of this that's not adjacent to the next piece. You've got a discontinuity. So Fourier, you're wrong." And Fourier said, "But no, it works out in infinity." And they said, "No, you're still wrong because even infinity, if these two things are joined together, if they're smooth and continuous, you can't make non-continuous functions. And what's worse, this square wave has an infinite set of discontinuous functions." So they denied him his PhD. And it wasn't until long after he was dead that another mathematician, Oliver Wendell Heaviside, discovered the proof of why Fourier was in fact correct. So as a quick review of what we've done so far, we started off talking about Laplace analysis at the beginning of the year. And that had an input that had some sort of step function. So as an example, it's flat and all of a sudden it starts doing this thing. You might remember that one. That looks something like omega squared over s squared plus omega squared as an input. And if you had an input that looked like that, and you put it into your transfer function, the way you'd find the result would not be to do that complex integral. You could do the complex integral out here, that convolutional integral, but instead the way we taught you to do it is to take its Laplace transform to find x of s, and then multiply it by the h of s so that you get an output y of s that's equal to the product of the input with a transfer function, and then you take its inverse Laplace transform to find your result. That was the first exam block. Now the second block that we just finished, I'll call the frequency analysis method. And that works with inputs that are sinusoidal steady states. In other words, phasors. And so now our input no longer looks like a cosine of 7t u of t, but just a cosine of 7t. It's sinusoidal steady state. It goes on forever. And we're going to put it into an h of j omega. It's just the same thing as up here, but with s replaced by j omega. And that gives us some response. And you know that if you put a sinusoidal steady state input into any linear system, you're going to get out a cosine of that exact same frequency. And the only thing that can change is its magnitude and its phase. And the crazy thing is that if you evaluate your transfer function at 7 to match with your input frequency here, you found that this is, in polar notation, has a magnitude and it has an angle where these magnitudes are the same and these angles are the same. And so using the frequency analysis method, it's not the same as Laplace analysis. You didn't multiply things, you didn't find inverses, but the system transfer function seems certainly very related. So here's Fourier's brilliance, and this is why we care about him. And what's a little bit confusing is that we call this Fourier series. There is another thing called Fourier transforms, but Fourier series says that the input here is any periodic waveform. So as an example, here's your square wave that Fourier's thesis team said would not work, and in fact it does. And this is all, again, chapter 17. If you can break up this waveform into a sum of this waveform plus a higher frequency waveform plus a higher frequency waveform, and we'll call this x1, x2, and x3. Well, hey, you've solved the problem. You can see now that you can just put this into your h of j omega, and that will give you an output of y1 plus y2 plus y3, where y1 corresponds to x1, x2 goes to y2, x3 goes to y3, and then all these together must sum to form your y output. The process of breaking any kind of random input waveform like this into a series of cosine waves, that is called Fourier series decomposition. And that's what we'll be talking about for several lessons. And then each of these will analyze. You'll analyze each using method 2 above, and then sum for the result. And we'll do that towards the end. So the big picture is if we can figure out how to do Fourier series decomposition, if we can figure out how to break apart any periodic waveform into a sum of sinusoids, then you already know how to do step 2. And now you can find the result of a circuit to any kind of periodic waveform. And this is huge, right? Before, the only kind of periodic waveform for which you could find a circuit output was what, Joe? What was the only periodic input for which you could find a circuit output?
Sinusoidal waves.
Sine waves, that's it. That's the only one. Sinusoidal steady state phasors. All right, any questions on this first part? So how do you go from this particular